controllable flow, and manipulation of liquid metals. This review summarizes the controllable flow and manipulation of gallium-based liquid metals. There are generally only a few ways to handle fluids, but liquid metals offer versatile control due to their properties. Number 1. Excellent fluidity. Number 2. Adjustable surface tension. Number 3. Electrically and chemically controllable surface oxides. Number 4. Metallic electrical and thermal conductivity. And number 5. The ability to alloy with other metals. For example, magnetic particles. These all-in-one properties empower liquid metals to exhibit controllable flow in confined microchannels. Steerable flow, like beam steering, and from nozzles, printable flow, and make liquid metals susceptible to various energy fields, including electric, magnetic, electromagnetic, wave, and light fields. Consequently, the flow and manipulation of liquid metals enables intriguing morphological changes, formation of droplets/plugs, jets, fibers, and controllable motion, jumping, bouncing, directional locomotion, rotation of liquid metals, with new fluidic phenomenon and practical applications such as soft electronics and robotics. This review aims to present a selective framework and provide insightful understanding for controlling and shaping liquid metals, thereby stimulating further research and generating increased interest in this topic. Liquid metals and their alloys are exceptional materials that possess both fluidic and metallic properties. Their excellent fluidity is primarily attributed to their low bulk viscosity, twice that of water, with low kinematic viscosity. This allows liquid metals to flow as effortlessly as water at room temperature. Leveraging their fluidity and high electrical conductivity, liquid metals serve as ideal soft conductors for flexible electronics when injected into elastomers. Their high thermal conductivity and non-flammability make liquid metals practically attractive for convective heat transfer in high-temperature applications with high heat flux density. A significant rise in temperature of liquid metals can be achieved due to their relatively low capacity compared to water for further manipulation. Moreover, liquid metals have negligible solubility in most liquids, making them compatible with other fluids in various devices without the risk of dissolution concerns. Another notable aspect is their ability to form alloys with other metals, resulting in alterations to their physical properties. For instance, alloying liquid metals with copper enhances thermal conductivity, while mixing liquid metals with nickel particles increases viscosity and renders liquid metals susceptible to magnetic fields. Such composites and alloys confer improved performance to the liquid metals in catalytic applications and energy storage, along with the potential applications in the biomedical field. Moreover, the surface properties of liquid metals can also be changed by coating liquid metals with nonmetallic materials. Non-stick surface by coating PTFE, WO3, and graphene. Detailed discussion and part of other methods. Table 1 summarizes some physical properties of gallium-based liquid metals, alloys, mercury, and water for comparative purposes. It also includes the alteration of properties for representative liquid metal composites. And here is Table 1. So we have the melting point, density, surface tension, viscosity, kinematic viscosity, and electrical conductivity. Now let's scroll down. To date, most reported reviews on liquid metals have focused on specific topics, demonstrating the experimental setup, material synthesis, structure design, motion, and applications in each topic, such as microfluidics, surface oxides, surface tension, 3D printing, soft electronics/robotics, and synthesis for new materials. However, few reviews have taken the perspective on controllable flow and manipulation of liquid metals. And here is this lovely image. We have microfluidics, surface tension, magnetic manipulation. You got a bead, paper, liquid metal droplet, permanent magnet, acoustic manipulation with a reflector wall, liquid metal, levitation plane, and resonator wall. Wall, like WALL. They mean intelligent reflective surface. Yes, we call it a wall. Light manipulation, laser on temperature gradient, dispensing and printing, electromagnetic manipulation, morphology, motion control, new phenomenon, and application. Now let's scroll down. Microfluidics. Owing to their rheological properties at room temperature, liquid metals can serve as an injectable liquid into microfluidic channels. In comparison to mercury, the distinguishing feature of the liquid metals discussed in this review is the rapid formation of self-limiting thin oxide layer upon exposure to oxygen. Although the oxide skin makes liquid metals behaving like an elastic material, liquid metals can flow readily once they experience a critical surface stress necessary to break the oxide. Figure 2a shows how liquid metals stop short of the entrance to a narrow channel below 85 kPa pressure, mercury on the right column, for comparison, but increasing the pressure to approximately equal to 89 kPa enables rapid flow through the channel toward the outlet. When the inlet pressure is relieved, liquid metal retains its stable shape, in contrast to mercury, which immediately returns to its initial state. The stability of liquid metal is attributed to the presence of the oxide skin on its surface. However, direct injection may cause leaks or delamination of complex channels due to positive pressure required. Moreover, the liquid metals only partially fill the corner and dead ends of channels. To address challenges related to direct injection, a vacuum method is employed to fully fill complex channels with liquid metals. This method involves covering a single inlet with liquid metal and subjecting the structure to a vacuum, which removes air from the channels and the surrounding elastomer. Restoring atmospheric pressure then creates a positive pressure differential, pushing the liquid metal into the channels and ensuring complete filling, including corners. The stable structure makes it possible to integrate electrodes of liquid metal into fluidic systems, while the structures become unstable under conditions that remove the surface oxide. And we're going to keep scrolling down. Surface tension manipulation. As mentioned above, liquid metals favors the formation of droplets due to its high surface tension. Surface tension is a crucial physical property of liquids that describes the attractive forces between molecules at the surface, tending to minimize the surface area of the liquid. The surface tension of liquid metal, an electrolyte, i.e., the effective interfacial tension, is alterable using effective methods. These methods can be categorized into two groups. Number 1, Redistribution of surface charges to create surface tension gradients. Number 2. Electrochemical controlled capillarity/oxidation. Electrocapillarity/electrowetting. Initially discovered by Lippmann, the interfacial tension of liquid metals, an electrolyte, is alterable upon application of an electrical potential, namely the electrocapillarity/electrowetting. Despite the distinction of the terms electrocapillarity and electrowetting, we consider them together due to their similarity in reducing the interfacial tension by redistributing surface charges in the electrical double layer at the metal electrolyte interface. The change in the interfacial tension is described by the Lippmann equation. Now, we're going to go over here and we're going to read. Artificial, synapse-based, intelligent light-controlled liquid crystal network actuators. Various forms of intelligent light-controlled soft actuators and robots rely on advanced material architectures and bionic systems to enable programmable remote actuation and multifunctionality. Despite advancements, significant challenges remain in developing actuators and robots that can effectively mimic the low-intensity, wide wavelength light signal sensing and processing functions observed in living organisms. Herein, we report a design strategy that integrates light-responsive artificial synapses with liquid crystal networks to create bionic light-controlled LCN soft actuators. Remarkably, AS-LCNs can be controlled with light intensities as low as 0.68 milliwatts, a value comparable to the light intensity perceivable by the human eye. These AS-LCNs can perform programmable intelligent sensing, learning, and memory within a wide wavelength range from 365 nanometers to 808 nanometers. Additionally, our system demonstrates time-related proofs of concept for a tachycardia alarm and a porcupine defense behavior simulation. Overall, this work addresses the limitations of traditional light-controlled soft actuators and robots in signal reception and processing, paving the way for the development of intelligent soft actuators and robots that emulate the cognitive abilities of living organisms. Sensing, learning, and memory are essential for artificial intelligence to replicate the cognitive abilities of living organisms. When the organism senses stimuli in the external environment, the nervous system regulates the function of the body through neurotransmission signals. For example, when we feel cold, the nervous system transmits signals to the body, which causes our muscles to contract, and thereby increasing body temperature in response to the cold environment. Within the field of biomimetic research, various actuators and robots fabricated from soft materials, such as silicone elastomers, hydrogels, liquid crystals, and shape memory polymers, are rapidly advancing fields. These materials exhibit reversible actuation and adaptability to environmental stimuli attributed to their flexible, miniaturized structures. Significant efforts have been dedicated to developing intelligent actuators and robots within research focusing either on replicating the structural designs of living organisms or emulating specific behavioral traits. Research on developing soft materials with biological intelligence is also emerging. Additionally, some functional smart materials featuring associative learning and memory have also been reported. However, it is still difficult for soft actuators and robots to mimic key functions, sensing, learning, and memory simultaneously as observed in living organisms. Indeed, it has been estimated that as much as 80% of the external information received by humans is derived from vision. Up to date, most soft actuators and robots utilize two primary mechanisms for light control. Number 1. Incorporating photothermal agents, such as carbon nanotubes, organic dyes, metal nanorods, or other fillers, to control the actuators and robots through the photothermal effect. Number 2. Using photodeformable materials to construct bodies, which are then controlled with ultraviolet light. Both mechanisms require high light intensity, typically exceeding 100 milliwatts, to generate sufficient heat or initiate photochemical reactions. Furthermore, these actuators and robots need specific light wavelengths for effective control, thereby limiting their application in unstructured environments. Additionally, their responses to light are often volatile, complicating the intelligent simulation of light signal sensing and processing functions that are essential to living organisms. Consequently, developing intelligent soft actuators and robots that can respond to and process weak light within a wide wavelength range remains a significant challenge. The retina is capable of analyzing and pre-processing the spectral components of light signals, a process known as chromatic adoption. In the human visual system, the retina detects light stimuli, converts them into electrical signals, and transmits these signals to the brain's visual cortex via a neural network, where they are transformed into visual perception. The brain then analyzes these signals and coordinates muscle movement through the nerves. This neural system not only triggers muscle action, but also processes light signals, learning, and memory. Recently, researchers have developed various artificial synapses inspired by the retina of applications in image recognition, bionic neuromorphic systems, and biologically inspired multimodule responses. These devices enable advanced bio-inspired color sensing and possess the capability for sensory adaptation. These properties help to enhance the adaptability of soft robots or actuators in unstructured environments, which is crucial. Therefore, it can be assumed that integrating a device capable of simulating biological neural activity into a conventional light-controlled soft robot could offer a level of intelligence that was previously unattainable. And here is this lovely image. Your brain is electrical. Your eyeballs only see 0.0035% of the electromagnetic spectrum. They are using optogenetics since 2005. There's Zigbee, and their Bluetooth, and these teeny tiny sensors all around us in the air molecules. The free space optical, the visible light communication, and they have based everything on biological mimicry, like you see with the porcupine. Now let's go over here, and we're going to read. Scientists harness liquid light to induce electrical current in superconductors. The key factor is entrainment between excitonic polaritons and electrons. Scientists at HSE, Moscow Institute of Electronics and Mathematics, have induced a superconducting current using liquid light, or excitonic polaritons, which are hybrid particles formed by interaction between light and matter, and possesses the properties of both light and material particles. The ability to manipulate an electrical system through an optical one can be valuable in the development of technologies such as quantum computers. When designing a quantum computer, conflicting requirements are imposed on its various components. For instance, a quantum processor should operate fast, whereas quantum memory must acquire and retain information slowly over an extended period, preserving it in a quantum format to prevent damage from environmental factors. Managing the interaction between these two systems poses a challenge that numerous physicists engaged in quantum technologies must confront today. Researchers at HSE University have investigated the drag effect between superconducting and/or superfluid systems in an unconventional hybrid system comprising two subsystems, a thin superconducting film and an excitant polar-Wrighton condensate. This image shows how mutual entrainment operates. A superfluid drag attracts superconducting electrons, leading to the induction of a current in the superconductor. Excitonic polar-Wrightons, also referred to as liquid light, represent an exotic state of light and matter, a thin semiconductor, trapped between two mirrors. In such a system, light alternates between existing as an exciton, a pair of electrons bound by the Coulomb force and a hole within a semiconductor, and running between the mirrors, which is how a polar-Wrighton operates. An exciton polar-Wrighton liquid exhibits superfluidity, enabling it to flow without energy loss due to friction. Russian researchers have previously considered a model in which a superconductor sandwiched between mirrors and a semiconductor interacted with excitonic polar-Wrightons. A team of researchers, led by Yuri Lozovic, professor at HSE University, hypothesized that, beyond the typical interaction, the mutual entrainment effect between a superconductor and excitonic polar-Wrightons might also be possible. Positioning a semiconductor between mirrors enables the generation of a superfluid liquid from the excitonic polar-Wrightons, and its flow can induce an electron current in a superconductor. The authors of the paper computed the potential strength of this effect using realistic parameters for modern semiconductor and superconducting materials.